This talk is about fractals and their geometry. So what are fractals? We'll ask, how long is the coastline of Britain? What are the snowflake curve and the Sierpinski triangle? And what are Julia sets and the Mandelbrot set? But before I introduce fractals, here's a story about a young Swiss alpenhorn player. He was madly in love with a young lady in his alpine village and decided to serenade her with his finest and longest alpenhorn. In fact, it was infinitely long, being obtained by rotating the hyperbola y equals 1 over x, where x goes from 1 to infinity, around the x-axis. But when he tried to play it, it wouldn't work. It had become rusty, and its inside surface needed a fresh coat of paint. And on calculating how much paint to buy, he found this to be an infinite amount. In desperation, he sought help from the village mathematician, who calculated the volume inside the alpenhorn and found it to be finite. The solution was now simple. Pour this finite amount of paint into the alpenhorn and then pour the remainder away, leaving a coating of paint on the inside. The young man did so. The alpenhorn worked perfectly. The young lady was delighted, and the young couple lived happily ever after. What's the relevance of this story? To answer this, consider the question, how long is the coastline of Britain? Viewing the map from far away, we might try to estimate the coastline's length. But as we zoom in to become closer, we find hidden bays and inlets and more twists and turns in the jagged coastline. And the closer we get, the larger and more accurate our estimates become, eventually growing without limit. So the coastline of Britain has infinite length, even though it encloses only a finite area. Rather like the alpenhorn, with infinite inner surface area, but enclosing a finite volume. The jagged coastline of Britain, with its infinitely many twists and turns, is an example of a natural fractal curve. We'll now consider two further examples, and we'll see how they share properties that challenge our traditional views of geometry. Many curves are smooth everywhere with no corners, like the curve at the top left. A simple example that fails this test is the V-shaped curve next to it, which is continuous, but has a corner when x equals 0. It's not difficult to draw similar curves that are continuous everywhere, but have corners at a finite number of points. But in 1872, the German mathematician Carl Weierstrass shocked the mathematical world by describing a continuous curve which had a corner at every point. In 1904, the Swedish mathematician Helge von Koch produced another continuous curve in which every point is a corner. This was his snowflake curve. To construct it, take an equilateral triangle as shown above on the right. Then divide each side into 3 equal parts and replace each middle third by the other 2 sides of a triangle to give a peak. This produces a star shape with 12 sides. Next, repeat the process on each side of the star to give the next shape. Continuing in this way forever ultimately yields the snowflake curve shown below, a continuous curve with corners everywhere. It also has other interesting properties. Because each iteration of the construction increases the curve's length by a factor of 4 over 3, the snowflake curve has infinite length. It also encloses a finite area, which can be shown to be 1.6 times the area of the original triangle. So, like the coastline of Britain, it has infinite length but encloses a finite area. The snowflake curve also exhibits self-similarity. Zooming into any part of it produces ever smaller appearances of the same pattern. This property of self-similarity at all levels is a fundamental feature of fractal patterns. Another well-known fractal pattern was introduced in 1915 by the Polish mathematician Wacław Sierpiński. It also exhibits self-similarity, with many smaller versions appearing as we zoom in to examine it in greater detail. To construct it, as shown above, we take a solid equilateral triangle, split it into 4 smaller triangles, and remove the interior of the inner inverted one, leaving 3 smaller equilateral triangles. We then repeat this process for these smaller triangles and continue in this way forever. An unexpected observation here is that we can also obtain the Sierpiński pattern from the well-known Pascal's triangle, part of which you can see on the right. To do so, we colour every odd number grey and every even number white, as shown here. Around 1975, a rather different approach to fractal images was being developed. Benoit Mandelbrot was born in Poland in 1924, lived for some time in France, and eventually settled in America. Here he introduced the term fractal, meaning broken, to describe these objects with their intricate nature and self-similarity. He called them rough or fragmented geometric shapes that can be split into parts, each of which is at least approximately a reduced size copy of the whole. He also memorably commented, "Beautiful, damn hard, increasingly useful, that's fractals." Mandelbrot's contributions to this area greatly influenced mathematics in the second half of the 20th century, as fractals came to influence a wide range of topics, from chaos theory to the study of planetary motion, and from the flow of air around an aeroplane wing to the diagnosis of cancer. To understand Mandelbrot's approach, we'll first consider linear transformations of the plane of complex numbers. These are numbers of the form z equals x plus iy, where I is the imaginary square root of -1. In these transformations, each point z is mapped to az plus b, where a and b are fixed complex numbers, such as the 2 examples below. Sending each point z to z over 2, where a is a half and b is 0, and to z plus I, where a is 1 and b is I. What happens when we apply such a transformation repeatedly? Starting with a given point z0, do its successive iteration z1, z2, etc. ultimately converge to a finite point, or diverge to infinity, or neither? In each case, the associated recurrence relation zn plus 1 equals a zn plus b takes us from each point zn of this iteration to its successor zn plus 1. For z maps to z over 2, with initial point z0 and associated recurrence relation zn plus 1 equals zn over 2, the first iteration halves z0 to give z1 equals z0 over 2. The second iteration then halves the result to give z2 equals z1 over 2, which is z0 over 4. The third one gives z0 over 8, and so on. Here, the successive points zn ultimately shrink to 0, whatever our initial point z0. For z mapped to z plus I, with recurrence relation zn plus 1 equals zn plus I, The first iteration sends z0 to z0 plus I. The next two then send it to z0 plus 2i and z0 plus 3i, and so on. Here, the resulting point zn diverge to infinity for all initial points z0. We next move on to quadratic transformations. Here, each point z is mapped to az² plus bz plus c, where a, b, and c are fixed complex numbers. But investigating these in general is rather complicated. Fortunately, a change of variable always simplifies these to z maps to z² plus c, where c is a fixed constant. So here, the associated recurrence equation is zn plus 1 equals zn² plus c. We can therefore restrict our attention to these examples for different values of c. And surprisingly, changing these has major consequences. For each value of c, we'll distinguish between the set of initial points z0 that stay finite after repeated iterations and those that diverge to infinity. The boundary between these two sets is called the Julia set, after the French mathematician Gaston Julia, who studied them in the early 20th century. When c is 0, above left, we have the transformation z maps to z², with its associated iteration zn plus 1 equals zn². This repeated squaring fixes the point 0 and sends the point 1/2 successively to 1/4, 1/16, 1/256, etc., which converge to 0, while sending z0 equals 2 successively to 4, 16, 256, etc., which diverge to infinity. And in fact, all the shaded points within the circle on the left shrink to 0. All the unshaded points outside the circle go to infinity, and the Julia set is the circle separating these. When c is equal to -2, below left, we have a very different situation. Here, every point on the line between -2 and 2 stays finite. Every point off this line diverges to infinity, and the Julia set is just the line segment itself. The case c equals -1 is even more bizarre, as we see on the right. Here, every point within the shaded region stays finite, every point outside it diverges to infinity, and the Julia set is the boundary of the strange region. So Julia sets vary widely for different values of c. Here are 3 more of them. Notice that the first 2 are connected, that is, they're in one piece, while the last one, sometimes called the seahorse, is not connected. It breaks up into many separate pieces. This difference turns out to be crucial. We at last arrive at the Mandelbrot set, a celebrated fractal pattern that arises in various ways. An early version had been presented in 1978, but it was Mandelbrot in 1979–80 who extensively analysed it by computer, describing it as an astonishing combination of utter simplicity and mind-boggling complication. As you can see, it's symmetrical about the horizontal axis and resembles a cardioid or heart-shaped curve, with infinitely many circular disks and other bits sticking out from it. As with other fractal patterns, it exhibits self-similarity in abundance. So how is this set defined? One way involves Julia sets. Most of our earlier Julia sets were connected, but the seahorse was not. Based on this idea, the Mandelbrot set consists of all those complex numbers C for which the Julia set is connected. So from our earlier examples, we see that the Mandelbrot set includes the points 0, -2, -1, I, and 1/4, but it excludes the point -3/4 plus 1/4 I. It also includes all real numbers between -2 and 1/4, but no other real numbers such as -3, 1/2, or 1. An alternative but equivalent definition of the Mandelbrot set directly involves the iterations of the recurrence relation zn+1 equals zn² plus c when the initial point z0 is fixed at 0. The Mandelbrot set then consists precisely of those points C for which all these iterations remain finite. The Mandelbrot set is highly complex. Indeed, Guinness World Records claimed it as the most complicated object in mathematics. As mentioned above, self-similarity is everywhere, and the more closely we examine it, the more convoluted its structure seems to be. Here on the right, you can see the amazing result of zooming into just one of its protuberances. The Mandelbrot set also exhibits great beauty and gives rise to a wide variety of intricate and attractive pictorial images. Described as fractal art, these date from the mid-1980s onwards and regularly feature on posters and t-shirts. This unexpected connection between science and art was a great joy to Benoit Mandelbrot, who had done so much to develop it. And with these beautiful pictures, I thank you for listening.